Welcome back to the Math Professors. If you enjoy content that can be found in any college math class, please consider liking, subscribing, and sharing. I'm Professor Van Hamlin, and I'm going to cover probability. More specifically, how to calculate the probability of and statements, and also how to calculate the probability of or statements. So, or statements are probabilities found in a single trial. So really what I'm asking is, what's the probability that I get this thing or this thing if I make a single selection? Now it depends if the events are disjoint, which means there's no overlap. We can also say that they're mutually exclusive, or they're if not disjoint, which means there's a little bit of overlap. That means that you're really in both sets at the same time. So if it's disjoint, the probability of A or B in a single selection is just going to be the sum of the probabilities. It's the probability of A plus the probability of B. Now, your OR statements, since they're addition statements, we're really trying to add the probabilities in such a way that we don't double count anything. So if there's some overlap, if I find the probability of A, some of that might also be in B. So we handle that by saying the probability of A or B in a single trial is the probability of A plus the probability of B minus any double counts. So this is the probability of A and B at the exact same time. So I have to subtract off this extra area because I've already counted it once when I did the blue and then once again when I did the pink. So I have to subtract that off. So in class, I usually just say the probability of A plus the probability of B minus the probability of both at the same time. Now, and statements they're a little different. They're not done in single trials, they're done in consecutive trials. So when I ask the probability of A and B, what I mean by that is the probability of A first and then B second. Now, if the events are independent, which means I'm selecting with replacements, it also means that the probability of one is not affected by the success of the other. So the probability of A first and B second is just going to be the multiplication of the probabilities. It's P of A times P of B. Now, if I'm selecting without replacement, which means if I've successfully grabbed something, I don't put it back. So now that thing is gone, which means now your sample size or your sample space is now changed a little bit. So we say that this is dependent. So the probability of A first and B second is going to be the probability of A. This thing still represents the probability of B, but this is the probability of A after B has been selected. After probability of B after A has been selected, and then that particular person has been or thing has been taken away from the sample space. So I'm going to do an example to where we do each one of these, some disjoint, some not disjoint, some independent, some dependent, and really kind of get to the heart of how to calculate these things. So given the survey results, I have a survey that I've collected the data and I've organized it in age groups. And also if they refuse to respond or they actually responded. So this particular 45 would mean that you're in age group 22 to 29, but you responded to the survey, as opposed to this one, which is you're in the same age group, but you refuse to respond. So the first two questions, I'm doing a single trial, and then the last two questions, I'm doing consecutive trials. So let's find the probabilities. So it says in a single trial, what is the probability of selecting someone who responded or is in the 22 to 29 age bracket? And then what I further ask is, are these events disjoint? So what we're looking at is, I can see that this immediately is an OR statement. It says it here. So I really need to know what is event A and what is event B. We know that the probability of A or B is going to be the probability of A plus the probability of B minus the probability of both, assuming they overlap. So let's see the responded. So this is going to be our event A, and then the 22 to 29 age bracket is going to be our event B. So when we have the probability of being, responding, or say 22 through 29, well, we know this is your A, this is your B, so it's going to be the probability of the first plus the probability of the second, so 22 minus 29, minus the probability of both, assuming there is a both. If there's not, this will immediately become 0 anyway, so it'll kind of work out to be the other equation. So when we want to find these probabilities, I need to know really, all these denominators. So then I can have the probability of the first plus the probability of the second minus the probability of both. So let's add everything. So add up this first column. This gives us 214, 54 plus 5 plus 45, plus 41 plus 30 plus 12 plus 10. Gives us 247. So I add those two together. We get a total of 461. So this thing has a full total, which is equal to 461. So that's going to be in the denominators of each of these. Because remember, when we're doing probabilities, it is basically your yeses over your totals. How many people live in that thing totaled over everybody. Okay, so now I have to figure out the first, or event A, which is going to be responded. Well, responded was the second column, so this is going to be 247. So let me color this up to make sure that you guys kind of understand what we're doing. So event A is going to be our responded. So when I look at responded, I'm talking about all the people that are in this group here. So I know that that's at 247. So this is 247. Now the next one I have to find, event B, and event B is going to be this 22 through 29, so event B is going to be right here. And when we add those up, you can see that that's going to be 75. Now we have to see if there's any overlap. Are you in the blue box and the pink box at the same time? We can see that that is true, and we can see that that's this 45 right here. So I'm going to have to subtract off that, that 45, this overlap. Now adding and subtracting fractions, we just add their numerators, keep the denominator. So this is going to be over 461, and 247 plus 75 minus 45 gives us 277. Now, writing this in 3 sig figs, so 277 divided by 461 gives us 0.6008, and that 8 is going to turn that last 0 into a 1, so 6008 or 01. Now, the last I ask, are the events disjoint? I know I'm squishing it in, but I'm trying to get all these examples in here. So, they're not disjoint. We can see that there is overlap. It's right there. So this is, these are not disjoint. You can be both at the same time. Now the second question says, in a single trial, what's the probability of selecting a person that is between the ages of 40 and 59? Now I selected this kind of wording because you see it in books all the time, and you immediately kind of see this word and, you're like, oh, it's an and statement. But we have to ask ourselves, what does this mean? Erase this blue, put it all back there. Okay, so being between 40 and 59 really would mean that you are in between particular brackets, that you are, well, where's 40 through, you're 40 through 59. Well, 40 through 59 is going to be, between these two things here. So actually, when we're talking about 40 through 59, we're not really saying an and statement, that this is actually the probability of being 40 through 49 or being 50 through 59. So if you're either in this bracket or you're in this bracket, then that means you're going to be in this total 40 through 59. So let's kind of see what event A represents. Well, event A is going to be, the probability of you being in your 40s. Event B is going to be the probability of you being in your 50s. So if you're in any of those two, then you're in this 40 through 59 bracket. So this is an OR statement. So this is going to be the probability of the first, so the probability of 40 through 49, plus the probability of the second, which is going to be 50 through 59, minus the probability of both. I know you might be jumping the gun here, like, Mr. Van Halen, there's not in both. Well, we'll see in a second here. this will actually kind of verify if this thing is disjoint or not disjoint. Well, I'm going to have the sum of these three probabilities, so this plus this minus this, and I know the total is 461 each time, 461, 461, 461. Now let's see for here. I know to be in this bracket, you can see that there's 52, that is your 40 through 49, so this is 52, and then your 50 through 59, which is the pink, is going to be 63. So this is going to be 63 on the total. So the probability is going to be whatever it is over the total. And is there any overlap? You know, do these boxes intersect anywhere? And they don't. So in that case, you know, this is going to have 0 in this overlap, really verifying that, you know, this piece is just going to disappear. Which is why the probability of the OR statement is just the probability of the first plus the probability of the second, because there are no double counts. Verifying that, you know, this is a disjoint set because this is equal to 0. So when we add these things up, we have 52 plus 63. Since I'm in the video, I'm going to double check. So this is going to be, you know, 115 all over that total. So divided by 461, we have 3 sig figs. I get 0.2494, so 249. So really about a 24.9% chance of happening, as opposed to the first one, which is about, you know, a little over 60% chance of happening. Now again, there is no overlap, I can see, because this disappears. So since there's no overlap, we say that this is disjoint. Disjoint means not joined. All right, the next two statements we're asking in two trials. So really, it's kind of the hint to say that this is likely going to be and statements. So the very similar idea up here. It says a single trial. It's also asking about disjoint. These are red flags that say we're probably talking about or statements. Same thing here. I asked if the events are disjoint. This is probably an or statement, and that's what, you know. Even though it looked like an and, it really was an or. All right. So the last two asks in single trials. What is the probability that we select a person who refused to respond twice? So really, I'm just asking, in two trials, what's the probability that they both refuse to respond? So what I'm asking for is, what's the probability of, you know, refused first and refused second? Now we have to ask ourselves, you know, are the selections being made with replacement or without replacement? You know, do you put that person back after you successfully select them, or do you not? All right, so let's see. So we have this is being selected with replacement. So that means if I successfully grab somebody, that means they are going back into the list of everybody after. So these probabilities will not be affected. All right, so the probability of refused and the probability of refused. Well, refused is up here, so this is going to be this list here. This is our refused. And I know the probability of refused is going to be 214, so this is going to be the probability of, this is the probability of refused, simply multiplied by the probability of refused, because I'm putting that person back. So the probability of refused is going to be 214 all over the total, which is 461, multiplied by 214 all over 461. You're welcome to multiply the fractions, or you can do it in your calculator. So 214, you know, times 214 is going to give us 45796, all divided by 461 squared is going to give us 212521. When you divide those, gives us 3 sig figs, 0.215. Now notice that this probability over here was not affected by the previous success, so therefore these events are independent. Now the last question is really asking the exact same thing, but instead of selecting with replacement, we're going to select without replacement. So very similar question. What is the probability of, you know, refused or refused? Well, this is going to be the probability of refused multiplied by the probability of refused after I remove one of those refused people. Because I'm selecting without replacement, I'm going to get rid of one of those particular people. So the very first probability, this probability of refused, is down here. This is 214 all over 461. Now I've successfully grabbed a refused person, so the refused to respond, I don't know where they are. This one now, let's say this one right here is now 35 instead, because I've gotten rid of somebody. So that means this sum, instead of being 214, is going to be actually equal to 213, because I got rid of one of those people. And if I get rid of one of the refused, that means I also got rid of one of the totals, so this is going to be equal to 460 as opposed to 461. So when you multiply these, 214 times 213 gives us 45582 divided by 461 times 460 gives us 2120960. You can see that this fraction is very close to this fraction. We're going to get a very similar number. Now, when you're talking about maybe smaller samples, this will look a little more dramatic, but we'll see if we even get rounded to 3 sig figs if we really get a different value. Not really, because this one, if I was going to continue, this would have been a 5, 4, 9, sorry, 8, 9, dot, dot, dot. And so that's why we round this to 3 sig figs, so 0.215. Now this one gives us a 0.21494. Ooh, geez, it's so close. 5. So, but this still rounds to, we can see that this rounded down to 5, and this will round up to 5. So you do get the same 3 sig figs when we're done, but they're not really the exact same probabilities. They are a little bit different. We see that this second probability has been affected by the success of the first, so we actually say that these events are dependent. So let's do one last example, because I want to show what happens if I ask for, instead of both of them being the same, what if one is something and the other one's this other thing if we have 2 events. So the last one I'm going to do is I'm also going to sample without replacement, but I want to talk about what's the probability, say in 2 trials, what's the probability of selecting a person who refused to respond first and then somebody in their 30s second. So this is still an and statement, so this is going to be the probability of, refused and then 30 through 39. And we know that this is multiplication, so this is going to be the probability of the first, so there are refused, and then multiplied by the probability of 30 through 39. Now, remember that this is being selected without replacement, so the probability of 30 or 39 is going to be affected by getting rid of a refused person. So this still represents the probability of being here, but knowing that we've dropped one of the refused by 1. So let's see what happens. So the probability of refused, we already know is going to be this 214 over the total, so this is going to be 461, multiplied by, now remember, I now get rid of a refused person, and I don't know where they live. They're somewhere in here. We're going to take our worst case scenario and assume that they're not in their 30s at the same time, so because there's a lot of other columns here. So what I can guarantee, not really guarantee, but what I can say for worst case scenario is that when we're asking for the probability of 30 through 39, well, this is going to be equal to 77. Now, I did get rid of somebody. I got rid of one person from the blue for sure, so instead of this being 461, this is now 460. So now when we multiply these things, our 214 times 77 is going to be equal to 16,478, and then 461 times 460, I have it down there, but this is 212060. So dividing these and giving me 3 sig figs gives me 0.0777. So 3 sig figs mean you start at your first non-zero number and take 2 more. And we know that these are dependent because we are selecting without replacement. And it's also dependent because you can tell that if I was going to ask for the probability of just being 30 through 39, it would be the pink, which is 77, over the entire total, which would be 461. But since I got rid of one of the refused, now you can see that's 460. So let's kind of recap this idea. These two with replacement ideas. Notice that down here I was asking for the probability of refused first and refused second. So, and then I did it without replacement. So I got rid of a refused person when I made this selection down here, when I successfully grabbed a refused person, which means there's one less refused and also there's one less total, because I'm asking for refused again. Now over here I'm asking for the probability of refused and then also 30 through 39, and since these don't match, you know, I got, this is the probability of refused, I successfully grabbed a refused, so now when I ask for the probability of something else, I only got rid of a refused, so that means there's going to be everybody in this group still there, because again I only got rid of a refused person. But I did get rid of somebody from the total of the entire group, so that's why it's going to be 77. Only the bottom changes here as opposed to where they both change here. You know, both of these went down by 1, but only here the bottom goes down by 1. So, if you like the content, please subscribe.